All right, yeah, that's it. Good, right? It's picking it up. Okay. Yeah, I'm gonna try going like a bit faster, just because like we lost a bunch of time. If I'm going too fast, it's like oh, okay. All right. So this is data communication 101. And quickly the agenda. First, we're gonna go over an intro to data communication. Like how data is represented flat, and how she transmits. And also quickly cover what endianness is, what a protocol is, and then talk about some of the characteristics of protocols like serial protocols versus parallel, async versus async, and directionality. And also cover network topologies real quick, and pull up slash pull down resistors. And then go over some common protocols like UART, I2C, and SPI. So first of all, what is data communication? It's the process of transferring data between devices through some kind of medium. So this can be like through copper wire, through like space, like over the air or something, um, etc. Like an MCU reading data from a sensor, or ground station sending software update to the satellite over the air, or the MCU writing data to the micro SD card. So all of these are just like you have your microcontroller and you need some kind of way to talk to these other devices in a way that it can understand and also read data from these other devices. And like how can I send a hello from one MCU to another MCU? And hopefully by the end of the workshop, you'll be able to understand how you can do this. So how does data look to a computer? Um, all computers see are just binaries, so either ones or zeros, and from that it has to interpret what that data actually means. So you need a way for all data to be represented in binary. So to encode information into a sequence of ones and zeros, you define like standards and rules so that you're able to understand it across devices. Like, oh, everybody like standardized that 101 means this. Like that a value of 65 in decimal translate to ASCII character of capital A. That's standardized, so if your device receives it and knows what that means. For example, like H is 72, which is binary 01001000. That 0B prefix is just used to like show that it's a binary number, and usually for hex we use 0x. And that's the ASCII code for like the letter capital H. Another example is like reset command, and that's a custom mapping from reset command to a binary sequence. So how do we transfer data between devices? Um, so computer and digital devices understand binary. So to send ones and zeros between devices, you need some kind of physical signal where you can encode ones and zeros onto. The focus of this workshop is going to be on wired communication. So sending ones and zeros by putting different voltage levels on a physical like copper wire. For example, putting 5 volts represents a 1, or putting 0 volts would represent a 0. Um, we can also do wireless communication, which we do like on our team in comms, but that's outside the scope of this workshop because that's a lot more complicated. And you can see like this picture here, like you write, this is like a different voltage level. There's different standards for what voltage level means a 1, what voltage level means a 0. This is for this example, like it was 3 volts for a 1, 0 volts for a 0. So they pull it up to like 3 volts for to indicate a 1, and then they pull the wire back down to 0 volts to show a 0. And that like data kind of like travels across the wire until it's like received, and another device is able to check the voltage level and see if it's a 1 or a 0. So electrical signals, typically in the form of voltage levels, are used to represent binary data. A simple way to do this is just like I mentioned, +5 is binary 1, as 0 volts, or ground is a binary 0. And like I said, the exact voltage level depends on different standards. And transmitter is the one that sets the voltage level of the wires based on the data it wants to send. And receiver just like checks what the voltage is to interpret that data. And change from high to low signifies like a change in binary state. So timing these transitions is pretty crucial to make sure that the data is properly interpreted and synchronized. Like you don't want to make sure that like you're checking the voltage level at the wrong time when the person who sent that data didn't mean for you to check it. So you need to figure out some kind of way to synchronize that. And there's also electrical noise that can cause errors when you're trying to interpret the binary state. So there's different ways to mitigate that, like twisted pair cables, shielding, differential signals, checksum parity. This is like all out of the scope of this workshop though. Like this can all be its own workshop. So we're not gonna go into this, but you guys can look into this. The reason like the electrical noise happens is just, like when you have a copper wire, like any kind of signals in the air will be picked up from by it, like because any piece of metal is basically like an antenna that's picking up signals. So that's gonna interfere with the data that you have on that wire, and that can cause issues. Okay, so quickly, endiness. So endiness is basically what the order of bytes is in your memory when you have multiple bytes. So like let's say you have um, like an int. On most systems that's 32 bits. So you need some kind of way to actually store that in memory, since in memory you have it like in terms of bytes, like 0 would be the first byte, memory address 1 would be the next byte. So you need a way to, since you have 4 bytes in an integer, you need some kind of way to order them. And endiness tells you which way they're ordered. With big endian, you have the most significant byte transmitted first, and with low endian, you have the least significant byte transmitted first. And like when we're talking about like communication protocols, and you can see like here in memory with low endian, you have the least significant bit at the lower address, since this like 0A is the most significant bit, and then or most significant byte, and 0D is the least significant byte, and 0D goes into like memory address A, while 0A would go into memory address A plus 3. And with big endian, it's just the opposite. So A goes into the lower memory address, and D goes into the higher. So like if you're trying to read memory, like the way you would read like a 32-bit integer normally, like a easy way to think of it is like big endian. If you're reading from lower memory to higher memory, it's kind of like the order you would see it in normally, and little endian is like kind of backwards. So if a receiver reads 32 a UN32 underscore T, which is 4 bytes from the wire, in the order 1, 2, 3, 4, like you need to know if it should be interpreted as 0, 1, 0, 2, or as 0, 4, 0, 3, 0, 2, 0, 1. These are each bytes. So 0A is like, this is in hex. So like in hex, each kind of like digit is 4 bits. So these two together are 1 byte. This is 1 byte. This is 1 byte. This is 1 byte. So in total, this whole thing is 32 bits. Any other questions? So we have some problems. First of all, how does the receiver interpret the voltage levels? We talked about this, like what voltage level means a 1, which one means a 0. Also, how does the receiver know where a bit starts and ends? like when I'm talking, like you can tell when I start my sentence and when I finish it. But it's not like that when you're sending ones and zeros, because like the bus is always going to be idling at some kind of point, and you don't know if that's actual data being sent or not, or like if it's staying at one, you don't know if that's multiple ones or if they just like forgot to change it or something. And how does the receiver interpret the bits? What's the endiness, and is there like some kind of metadata? How does the receiver know when data is being sent? How does the receiver actually validate that the data isn't corrupted because of noise or something, or if it's the original data? And the solution to this is to use a protocol, and that's what we have. So, protocol is basically a set of rules that just define and standardize how devices communicate with each other. So if you buy a device and it says like it communicates through SPI protocol, like you know exactly what it's expecting, how it's going to output its data, and everything. So it ensures that data is transmitted, received, and interpreted correctly across the network, and make sure that there's interoperability between different hardware and software systems. And they exist. Protocols exist at like all layers of the OSI model, and some of them define rules for multiple OSI layers. Um, we're not going to cover OSI model in this workshop, but it's in the firmware wiki if you're interested in learning. So some popular examples of protocols are like I2C, SPI, CAN, TCP, IP. You guys probably heard about this. It's like IP is the internet protocol. HTTP, which is like when you open up a website. This workshop is going to focus on protocols for sending data one bit at a time, um, aka serially, between hardware devices that are electrically connected. What's the difference between serial and parallel? Serial, you're transferring data sequentially, one bit at a time over a single wire. Whereas with parallel, you basically have multiple wires so that you can send multiple bits simultaneously, and each bit has its own wire. So like you can see here, in the bottom example, it's a serial. So you have one wire. And first you send like imagine that D is like a byte. So D0 is the first bit. So you send the first bit, and then after that you send the second bit, and the third, and so on. Whereas with parallel, you basically have like your each bit of your byte has like its own wire, and that way in like one go you can send that entire byte, and then the receiver can interpret that back on the other side. So usually, because like parallel takes um, a lot of wires, serial is easier to implement, and it's cheaper and less complex. But parallels obviously a lot faster since you can send multiple bits at one time. And this is why usually like a lot of processors like in their like internal memory they'll use like a lot of parallel interfaces. But if you have like some kind of external peripheral, you'll usually use like some kind of serial protocol. So what's the difference between synchronous and asynchronous? Synchronous, your sender and receiver are synchronized by a shared clock signal. So remember how I mentioned before about how you need to know when to actually check the voltage value, and know like if it's been like at one for a while, is that multiple ones, and like how many ones is it, or is it just like meant to be one bit? So the way you do this is by synchronizing it for synchronous is by synchronizing with the clock signal. So at one like edge of the clock. So edge is basically when the clock, oh, this is the clock, right? Uh, when the clock changes from like 0 to 1 or like vice versa, it basically just changes this like binary state. That's an edge. So the sender would know on which edge it can change the signal, which is the data line, and the receiver knows on which edge to sample the signal. Like for example, you could have it like the sender will only change the signal on the falling edges, and every rising edge, the receiver knows that the data is ready and it can sample it, and that data stays until the next falling edge, so that the receiver can check that voltage and um, like kind of like read it and interpret it. Does that make sense? Or anybody have any questions? The clock line is like it's like a wire that's physically connected between the two, and the line is like going up and down, and there's like hardware that you like use to make sure that you only sample it at a certain edge of that clock signal. Any other questions? Yeah, I'll get into async in a second. Yeah. Okay, so with asynchronous, your sender and receiver are working independently. So you don't have data sent on a common clock. So obviously, since these are both like actual devices, they'll have their internal clocks, but they don't have like a wire connecting them that has a clock on it that's telling them when to like sample the signal and when to change the data. Um, so you need some other kind of way to like determine if the sender can change the signal or if the receiver should sample the signal. And like one example of a way simple way to do this is like predefine a baud rate. Baud rate is just like how many like bits you're sending in like a certain period of time. So you can say like, oh, I'm gonna send 1 bit per second, and that's predefined. Both devices know that beforehand that there's only gonna be 1 bit per second. So now each second I can just check, okay, what's the bit, and if I'm the sender, like I can like wait, or like we can say like in the first half of a second, this you can like sample the signal. In the second half, the sender will be changing the signal. So in the first half, the receiver knows, okay, I can read the value, and the second half, the sender can change the value because it knows it's not being read at that time. And that's how UART does it, and we'll get into that later. Okay, any other questions about that? If you're online, by the way, I probably can't see your messages if you're sending any, so you're gonna have to unmute if you have any questions. All right. So directionality. So there's um like three different like categories of this. So first we have um this is just like some quick terminology before we get into the protocols. So first we have simplex, which means that you only have data transmission in one direction. So one you have one receiver that's like just always receiving and one transmitter that just transmits. For example, with like a radio broadcast, the station just keeps like sending you like the radio signals and you're just like receiving it. There's no like two-way communication. It's just like all one way. Um, yeah. And then half duplex is where you can have data transmission in both directions, just not at the same time. So like for example, like when you're using like a walkie-talkie, how you'll like say something, it'll be like over, and then you switch to receiver mode to hear what the other person's saying. So you're both able to talk to each other. Like it's not just one person talking. You're both able to talk now. It's just not at the same time. Like one person needs to talk and then switch to receive, and then the other person can start talking. And then finally, we have full duplex, which means that you can have data transmission in both directions at the same time. For example, like when you're on a phone call, it's not like a walkie-talkie where you have to like explicitly say when you're done talking and then switch to receive. You're both just like talking at the exact same time, and you can like talk over each other and stuff. So that's full duplex. Okay, and then quickly some network topologies. So point to point is like when you have one device is connected to exactly one other device. Um, for example, right now, like my laptop's connected straight to the TV. That's like a point to point connection. It's just like a HDMI cable connecting my laptop to the TV. And so they're just like connecting, they're like communicating directly with each other. Then there's also a bus, which means you have like a shared cable or group of cables, and then you have multiple devices connected to that one cable that's shared, and they use like that shared cable for communication. And then you have star where each device is independently connected to a central device, and everything's routed to that through that central device, kind of like a Wi-Fi router or something. You have multiple devices connected to it, and then it connects you like to the internet. And then you can also have hybrid, which is like a combination of multiple of like these simpler topologies we mentioned. Yeah. Yeah. Um, and now real quick, pull up slash pull down resistors. So how do we make sure that the bus idles at a certain value? So when no device is like actively trying to send data, you want like the bus, it can't just be nothing. Like voltage always has to be some kind of value. Either and this will be interpreted as either one or zero. So the way you make it idle is with like a pull up or pull down resistor. Um, so you connect the bus to VCC, which is like a logical high voltage. You represent that with VCC. So like if you were using a protocol where 5 volts is means a one, then you would call 5 volts like VCC. Or ground, which is a pull down resistor, to make the bus idle at that value. The reason you need a resistor is to make sure that you don't get a short circuit. Like if you didn't imagine if you didn't have a resistor here, in this is like a diagram of an I2C bus. So if we didn't have a resistor here, and this I2C master 2 tried to like send a zero, it would essentially be grounding this line. But now we have no resistor, we just have a short circuit from like 5 volts straight down to ground. So you're gonna get like insanely high current since you have zero resistance, and that's gonna damage the bus. So you need that resistor to make sure you don't get that like insane um, like current through it. So usually with these pull up or pull down resistors, it's like an electrical thing, but usually they're like between 1 and 10 kiloohms, and like it's generally like a good idea to start with 4.7 kiloohms and then see the signal and swap it out with different stuff if you need to. The reason you need to swap it around, I won't get into the physics of why this happens, but like if you have too strong of a pull up, like you can see here in this example, you kind of get like a weird signal. Like you're not getting proper like rises and edges like you would see normally, like straight switches from like 5 volts down to 0 volts. Like it's kind of like just like weird and noisy and stuff. And if you have a weak pull up, you could get something like this where it's not able to switch edges fast enough, so you just get like a curve when you try to pull it high. And so this is why like you might need to try around different resistor values. Any questions about this before I move on, or anything before? Oh, we like. Oh, wait a minute. We talk about the end if we need to. I feel like it's kind of out of scope. These transistors. But yeah, if you're interested, you can also look into like what open drain, uh, like yeah, open drain, open source, open collector, open emitter, that stuff is, and like push pull. It's kind of out of the scope, but you can look into that or time it's related to this. And it talks about like how you actually like drive this bus line higher load, and that's like internal to your devices. Yeah. Uh, what do you mean? Like, yeah. Yeah, so you have a pull up resistor on the bus to pull it to some certain value, and inside each device, you would have like some kind of transistor usually, so that when the device um, isn't trying to actively send a signal, the transistor will be at like a high impedance state, so it won't affect a high impedance, like high resistance, so it won't affect what value it is on the bus, and the bus will be completely dependent on the pull up or pull down, and that's like what open drain, open source are. So you can look into that. All right. So now we're gonna talk about UART, which is a very common serial protocol. So for the physical layer, you can have signal levels varying depending on the implementation, but usually you'll have like 5 volts or 3 volt, 3v3 TTL. So like 5 volts is a one, 0 volts is a zero, or like 3.3 volts is a one, 0 volts is a zero. And obviously with these, there's like certain like thresholds. Like it's not gonna be like, oh, it's 3.29 volts. That doesn't count as a one. Like it will usually like count it down to like 2.8 volts or 2.7 volts. It'll still count that as a one, just to account for noise and stuff. Um, and you have like two electrical connections between the two devices. So you have TX connected to RX and vice versa, where TX sends data and RX is where the device receives the data. And usually with UART, you have a point to point connection. How long have how long has it been happening for? Wait, are you sure? Yo, can you hear me? Can't hear us? No, I can't hear you guys. Oh, I can't hear you guys. Uh, oh, I think it might have like switched my. How do I send video? Oh wait, where's the sound settings? Can you guys try talking now? Hello? Okay, okay, there we go. My bad. Yeah. All right, just go through all the questions right now. I don't know how many there were. Um, like I had a question like way back in like in the climate. It was the so like it's not about this um if there is no clock, you have to predefine it. So usually you would define your baud rate as like bits per second, and then your device would just like interpret that, like you just divide one by that to figure out the frequency of the data changes. Um,
For example, in the diagram, usually your bus will idle at a certain level. For example, in the diagram, it's idling as high, and the first bit that goes low is essentially denotes like, hey, I'm going to start sending some data to like the receiver.
yeah. So then once your the device sees it goes low, then it will be like, okay, now I'm expecting data at like one divided by the baud rate hertz, and it'll start sampling it. Okay. Was there any other questions before? Yeah. So when I say idle, I mean like if none of your devices are trying to use this bus, like they don't have any data they're trying to send on there, like none of the devices, so the bus isn't being used, it'll be held at some constant value, so that like you don't have it like floating and accidentally like goes to like a zero or something and so device reads it as data. You just like hold it at like one. So like before, like George just mentioned, like that example, with this example, you have it being held idle at a one, so that when eventually a device does pull it to a zero, you know data is being sent, because you knew that before it was just idling at one from the pull up resistor. That answer your question? Yeah. Any other questions? All right. Back to UART. So it's like I said, it's a point-to-point connection. So you just have two devices connected directly to each other. So like this device, its RX line will be connected to this other device TX line directly, and vice versa. And then you have in this example, like the ground directly connected to each other. So some of these characteristics, the data is transmitted serially. So one bit at a time will be sent over the TX bus, and it's asynchronous, so there's no clock signal. So you're gonna have to pre-configure a baud rate with start and stop bits, which we'll talk about in a second for synchronization. So like if you're using like your laptop to like read data like over UART from the RM46 and you have it connected, like your application would usually like ask you like what to set the baud rate to, and you would set it to the whatever baud rate the RM46 is using, so that you can make sure that it's able to synchronize itself properly. And usually with UART it's full duplex, but you can configure it in simplex mode as well. If you wanted to configure in simplex mode, just like get rid of one of these RX lines or one of these TX lines, and you just have one TX connected to another RX, and it's simplex. Yeah. For the framing. So first of all, like with protocols, like you have packets, um, or frames, which define like the structure of the data you send. Um, because like there's like extra, like there's a data you want to send, like that, to like communicate, and then there's also like extra overhead you have to add to make sure, like for stuff like errors or like making sure the device knows when to start sampling the bus, and like a bunch of other stuff. And so each protocol has its own frame that defines the structure of those packets. So for UART, you start with a start bit um, to tell the receiver that a new frame starting, like we mentioned in the other example, which is usually a single bit in the low state. Um, so like if we go back here, right here, where this data line goes low after being idle, this is a start bit. So like the device, like the UART receiver, could like it could just be waiting to see when the thing's pulled low, and as soon as it's pulled low, it knows that you're gonna start sending data now, and it's gonna have to start sampling. And the other time, it's just like chilling and doesn't have to do anything.
Also, how does it know when the bill is over? Like when the data is over?
Sorry, could you repeat that? You're kind of like cutting off.
Sorry. How does it know when the data being sent is
It's yeah, we'll get to that in a second. Ask it. Yeah, once we get to stop bits, ask it if you're still confused. Okay, so after the start bit, you send the 5 to 9 actual data bits. So this is the actual data you wanted to send, which can be configured as 5 to 8 bits. Like, so if you had 8 bits and I wanted to send like the letter H to George, um, the way I can do it is like H has like I mentioned before has some kind of binary representation, which is 8 bits. So you would send the first start bit, and then it'd be the 8 bits that represent the letter H. And so George would only want to like interpret those 8 bits as the actual data part and not as the packet part or like overhead. And then after the data bit, you can have 0 to 1 parity bits, which are optional. And this has to be configured beforehand, just like the baud rate, if you're using parity bits or not. Same with like the 1 to 2 stop bits. You need to configure those, how many stop bits you're using. So parity bits just used for error detection. It's kind of out of the scope of this workshop, but you can click on this link after to see more info. It's kind of just like it's just like one bit that helps you detect if there was an error or not by doing certain operations on the data that you receive. And then after the parity bit, you have 1 to 2 stop bits to signal the end of a frame. And so this gives the receiver time to process the data for the next frame gets here. And it's usually like 1 to 2 bits in the high state. So if I go back to this example, first of all, like the because this packet has to be like predefined. So you need to predefine how many start bits you're using, how long the data bits are going to be, how long the parity bits are, or if you're using them, and also how many stop bits you're going to have. And then obviously you have to configure the baud rate as well. All that needs to be pre-configured so that your devices are able to communicate with each other, and that needs to be the same between both of them. So if we go back to this example, so you have the bus idle at first, and then the bus master, which is like the device that's um, like controlling the bus, it'll pull the bus low for the start bit, and then you have the 8 data bits, which is just like whatever data you wanted to send, and then you have the parity bit for which can be high or low, and this is like optional, like I mentioned. In this example, they're using it. In this case, it ended up being low, and then you have 2 stop bits. So the receiver would see like, okay, here's the start bit. Now I need 8 data bits, and it's like, bam, 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 here, data bits, and it's like, okay, here's a parity bit. It's gonna use this to check for error, and then it knows, okay, now it's 2 stop bits, which means we're done, and it's back to idle. Any questions? Ryan, did that answer your question or
Yeah, thanks.
okay? Any other questions?
Yeah. Um, so in order to check for the start bit, do I need that?
Um, so it's like you wouldn't actually do that in software. That would be a hardware thing. I'd imagine there's probably like some kind of exception or interrupt that gets triggered when it gets pulled low. Because the UART controller would be like it wouldn't be in your MCU that interrupt happens. You kind of have like a separate little small device, like a UART controller, that would know as soon as it like that thing goes low, it'll start sampling the bus for the next like bits, and then that triggers. If you have interrupts enabled in your MCU, it will. Yeah, but like in the like you can imagine it like you have like a your actual MCU which you're writing code for, and then like it talks to like this little like internal module in it which is like a UART controller, and in that UART controller, when the data bus goes low, there will be an interrupt in the UART controller that'll tell you to start sampling, and then it will read that data and send that to your MCU. Any other questions? Yeah.
We use a state machine.
Basically, so that would be like the little module that would be like a little circuit in your MCU, or sometimes it's even like an external chip that you can like, solder on and create wires to connect your MCU to, and then usually inside those like circuits, there's like a state machine like running constantly, checking for like the start bit and stuff. Uh, yeah, but like that would usually that gives a lot of work to the MCU, and you want the MCU to do other work rather than always like data processing. So usually you offload it to like this single circuit or chip.
Yeah, and that circuit would be like basically just like pure like hardware. Usually, yeah, like ASIC.
Wait, so I have a, so is there just one protein one at a time? Basically, like, I'm wondering, if there's only one thing that you have, how does
Yeah, so like we mentioned, like the your controller would be like a separate little thing, so you're able to run your like thread of execution, like run your code, while you have like another module because it's just like hardware. So your hardware is like receiving and like storing that data is receiving over UART, and then you're executing your code at the same time. And then when you actually want to like read that value that you received, that's when you have to have some kind of code to read from that hardware and read that value into memory. Any other questions? So quickly, some of the advantages and disadvantages. First of all, UART is really simple. It's like it's RX and TX. It's low cost and really easy to implement since it's just two wires. But some of the issues is limited speed and range. Range is like every protocol like will have its certain like range that it works in. So like for the E people, like you don't want to be making all your traces for like UART and all your protocols super long, to the point where like it exceeds that range that they're good for, because then you're like introducing it to extra noise and stuff, and like the signals won't be as clean. Um, and UART also has a lack of built-in error detection mechanisms. Because like you have a parity bit, but parity like a single parity bit isn't that great, and there's other kinds of errors that won't be detected, like if the receiver didn't actually receive the data. Like you're just like sending data, but there's no like the receiver isn't like necessarily telling you back if it got the data or not. You could just be sending it, and the receiver's just never receiving it. Okay. Any last questions on your? Okay. I2C, also known as inter-integrated circuit. So similar to UART, for the physical layer, it can vary between implementations, but usually it's like 5 volts or 3.3 volts TTL. And with I2C, you use two different wires. So you have SDA for data, which is like serial data, and then you have STL, serial clock, for the clock signal. You can see that here. So there's the bus, and this is like a bus topology. So you have a master, then you have multiple different devices all connected to this shared bus. And the bus just consists of this data line and this clock line. And by the I2C standard, every line is always pulled up with pull-up resistors to make sure that the default state is high. And then this makes sure that like each device only needs to be able to drive the bus low by grounding it. So if you're designing some kind of device that's going to be using I2C, you don't need to add some kind of like logic or hardware to make it able to drive the bus high to send a one. All you have to do is just like let go, like stop driving the bus, and it will automatically be like back to its default state of one, and you only have to ground it to drive it to a zero. And then in terms of topology, like I mentioned, it uses a bus topology. So you have the master device, which initiates and drives the communication, and the master is always the one that generates the clock signal. And then you have the slave, which responds to the commands that are sent by the master device. And you can also have multiple masters and slaves connected to I2C bus. You obviously need to make sure that like multiple of them aren't like trying to use it at the same time and conflicting with each other. That's also one of the things that's nice about having I2C stat. Like I won't go into too much, but like that's one of the things that's nice about I2C always being like, since everything is only ground drive, it's only driving it low. If two different devices try to drive it low, or like one tries to drive it high, another tries to drive it low, um, like you're gonna have an issue with the data, but like you won't have some kind of like short circuit issue since one of them is just like not gonna be driving it to drive a one, and the other one's driving it low. Like that's not really an issue. And some of the characteristics, again, it's a serial protocol. Since this is a serial protocol workshop, um, it's half duplex, so you can only send data on SDA in one direction at a time. Obviously, since like with UART, it was you had two different wires for RX and TX, so you could have one value on RX while there's another value on TX. So this allowed you to have full duplex communication. But like if you only have one wire, like it can't be both a one and a zero at the same time. Like this isn't like quantum or anything, so yeah, it's only gonna be in half duplex. And synchronous, since we have a clock signal that tells the slave when to read the data, using like the edges of the clock signal. So like you can see in this picture here, up here in the yellow you have, and in green you have the data being sent. So the clock just like keeps like pulsing up and down to tell you when to like send and sample the data. And then you have the data line, which is like controlled by the master, and it's just that the bits that the master wants to send. So for the frames, usually to start like the current packet, you would have the data line pulled low while the serial clock is still high. So you can see that here, like in this example, like you can see the clock line is still high and the data line is pulled low, and this lets the receiver know that you're like starting a new transmission now. And with I2C, um, the way you know, since like we mentioned here, like again, hello, hello, what's going on?
Hello.
Okay, can you, when did I cut out?
When you explain
This thing?
yeah.
Okay, yeah. So I was just saying, like the clock, like in yellow here, it just goes up and down, at like a certain rate consistently to tell the transmitter when to change the signal and the receiver when to sample the signal. And you can see the data line here, which is just the bits that the master is sending, or the slave, whichever whoever's sending the data. Um, it shows like the data that is being sent. So like you can see when it's high, this is a one, and then it goes low to represent like a binary zero. Yeah. Okay. And then for framing, same with UART. Well, different because you have a clock, but like you have the data line pulled low for the start condition. And for I2C, you want to do this while this clock line is still high. So you can see here in this example, like you have the data line pulled low for the start condition while this clock is still high, and this lets the receiver know that a data transmission is starting. And since we, like I mentioned before, we have this bus configuration, we need some kind of way to know if, like, when data is put onto the bus, we need to know if they're trying to talk to us or trying to talk to somebody else. Like if, like in real life, you would like say somebody's name so they know you're talking to them. And that is kind of like similar. And here you have addresses. So each of these devices would have their own address. So I would first start off with their address, and then they can check they can read that, and if it's their address, they know to start listening. And if it's not, like they can just ignore it. Like if it's like it's if if I like start my sentence with like "Yo George," and then I continued like you already heard that I was like talking to George at the beginning, so you kind of just like ignore the rest. But George heard his name, so he'll start listening now to whatever I'm saying, and that's basically what the addresses are. So you can have 7 or 10 bit addresses, and that's just like I said, our way of choosing which slave device you want to communicate with. And also, as a quick note, you guys, if you're on firmware, you probably saw this in the onboarding. A lot of devices have ways to configure this address, so that you don't run into an issue where like two devices have the same address. Like if there's like two Georges in the room, and I said "Yo George," they wouldn't know who I'm talking to. Same issue. So you have a lot of devices have some kind of way to change the address, so you don't get that issue. Like in the onboarding, the temperature sensor, the way it did this is by just it had like certain external pins that you could tie to VCC or ground to set certain bits of its address to 1 or 0. That we can like if you had like the exact same address array, you could change 1 bit, and now you're chilling. Um, yeah, and there's also other ways too. Like there's some devices I'm pretty sure where like it starts with a default address and you can like change it like just by like writing data to it, write to a certain register. Um, and so after the address, you have the read write bit, which is gonna be 0 or low if you're doing a write operation, or 1 if you're doing a read. Um, So like write is like if I'm trying to write to some register like memory in that device, or read if I'm expecting that data, if I'm expecting that device to send some kind of data back to me. So after the read write, the receiver, um, after the address and the read write, the receiver whose like address it was would set this acknowledge bit. So remember how I mentioned like the data line is half duplex? So both the devices are able to drive this line. So up to like from start 7-bit to read write, this would all be set by the master, and now it would like release control of the bus for the slave to set this acknowledge bit. And this is like you can see in the diagram, this is going to be low. So this uh, bus master would, after the read write bit, it would just like let go of the bus and it'll idle back high, unless the device that you were talking to explicitly pulls a low to acknowledge that I received the address that you sent and the start and read write bit. So then you have the 8-bit data packet, which is again like the actual data that you want to send. And you can send as many as you want with acknowledges after every packet. So you could send like 8 bits, then acknowledge, then another 8 bits, and then stop, or you could do like 8 bits and then stop, or like send 8 bits, acknowledge, 8-bit, acknowledge, 8-bit, acknowledge, and then stop. Um, and then again, at the end, you would have a stop condition, which is just the data line being pulled high while the clock line is also high. So both of these, like the start and stop conditions, both of them need to happen while the clock line is high. And some quick notes, like I just mentioned, you have a repeated start condition where the master device can set the start condition again to start a new communication without actually releasing the bus. And then also you can have something called clock stretching. So like let's say we wanted to um, do like we wanted to do like a read from some kind of device. So we would send like its address and send the data and stuff. Um, and or we would send this address, I mean, and we would wanted to send the data back, but like it would need to first like process the bytes it received, and like maybe it needs to do some kind of other logic before it's ready to send the data back. So if the device needs more time to like send the data, it's allowed to just hold this clock line low to delay the master while it finishes processing. So it could like let's say it needed like 5 seconds. That's a long time, but like let's say it needed 5 seconds to process the data and be ready to send the data back. It could hold this clock line at a low value for 5 seconds. That way the master knows like the bus isn't high yet, it's trying to like start reading it yet. And then once it's ready to start sending data, it'll release the serial clock and it'll go back to pulsing, so that and then it'll start sending the data. Any questions on either of this?
Yeah, that's a good question.
Yeah.
How would
That would probably need to be a good question. That'd probably be
That depends. So it's really up to like the designer of the chip. Like if let's say the designer of the chip knows that it takes a certain amount of time to process the data, then um, it would include a clock stretch. It's more of a like behavior that some chips actually like will show kind of thing, and it will be mentioned in like a data sheet like for the chip. So,
Could you guys hear that? Okay. Yeah. Did that answer your question? Yeah, you wouldn't do that in software. That would be like when the people that are designing like that chip, they would know like, oh, this operation is going to take a while. So in the hardware, if you receive this and you're trying to send this data, know that you're gonna have to hold the clock line low before you're able to send that data because it's gonna take some time to process. All right, any other questions? So like, you remember how like the um master is the one sending the clock signal. So while this clock signal is being sent, if your address wasn't mentioned, the other devices are gonna be like just ignoring and like waiting for the bus to be released. Um, so the master can just like keep this clock signal going, and send another strike condition, so that it doesn't allow like any other devices to see like, yo, the bus like the clock stopped, so they're done communicating, and then they start trying to like jump in and do whatever they need to do. Since like remember we can have multiple masters on this bus, so that one master can just like keep the clock going and say that it's still holding the bus, so I can continue with its communication. Yeah. So the I2C address, for like a peripheral, it would be like set when it's manufactured and like mentioned in the datasheet. And also, if there's any configurable bits, that will be also mentioned in the datasheet. Um, but yeah, like in the ideal case where you get like a bunch of peripherals that are all manufactured with like separate addresses, you could have up to 2 to the 7 different peripherals connected on one bus without having any address conflicts. Okay, anything else? Advantages and disadvantages. So again, I2C is pretty simple and cost effective. To implement. It's just 2 wires again, and can also support multiple master devices. And like I2C, like simple, like if you're doing electrical, since it's only 2 wires, it's easy to route it. And disadvantages, it's limited by bus length and speed. So I2C can't have like too long of a bus, otherwise the signal won't be clean anymore. And it's also not as fast as something like SPI, which we're about to talk about. And also, it's only half duplex, so you can only have communication in one direction at a time. It can't be like simultaneous. And also, because you have to like send this address first, there's a lot of overhead. So like if I only want to send 8 bits of actual data, there's all this extra bits I have to also add, just to send those 8 bits. So that's what overhead is. It's just like extra bits that you have to send that you don't really like want to send, but like you have to. Okay. And now SPI, which stands for. Sorry. Yeah. Go ahead. Except for clock stretching. Yeah, well, if you're starting the clock signal or you're starting like with the start bit, um, that means that you're the master because you're like initiating the communication. You're the one that wanted to start the communication, and the slave is the one that's responding to you. Yeah. So your master, like before, like you vote, you sent the address, and then you vote some like 8 bits of data to set the. Actually, I think it was like 16 bits of data to set the pointer register, and then after that you could do another time where like you sent the address, but this time it was a read, and then the temperature sensor would send back the temperature data. In both cases here, like you were the master and the temperature sensor was the slave. Yeah, you would have to send that again, and change this time. Have the read write bit be low to indicate a write. Okay, all right, last one, SPI. Again, TTL logic levels, and then usually depends on the device, but for ARM 46 is 3v3. And SPI has four primary wires, so this is the most of the other two. So you have MOSI, which is master out, slave in. You have MISO, which is master in, slave out. SEK, again, serial clock. And then CS, which is chip select. So MOSI is used to transfer data from master to the slave, hence the name. Like the data is going out of the master and into the slave. And then MISO is the opposite. It goes out of the slave and into the master. And again, clock is just the clock signal used for synchronization. And then chip select is since SPI doesn't have addressing like I2C, you have another wire which the master uses to say which slave device it's talking to. So each slave will have its own chip select, which is controlled by the master. And this way we don't need to have addressing, and this saves us like those 8 bits that we normally would have had to send for the address. So like if I wanted to like choose which device I wanted to talk to, since each of them have their own clock signal, I can just set that certain clock signal to low, and now it knows that like it's being communicated with. And then topology, it usually uses a bus topology with like the stereo clock, MISO, and MOSI. You can see this thing in this diagram, this SDI. That should mean slave data in, so that's the same as MOSI, and SDO slave data out, the same as MISO. So usually the clock, the MOSI, and the MISO will be shared between all of the devices on the bus, but each device will need its own chip select signal, which will be separate. Um, if you use daisy chaining, then you don't need chip select for each device, but that's outside the scope of this workshop, so you can look into that if you want. And that allows you to not need like a whole bunch of different chip select lines. And typically, it will involve a single master controlling multiple save devices. And yeah, like I mentioned, they share MISO, MOSI, and clock. So some of the characteristics, it's a serial protocol. It's full duplex since you have separate lines for data going out of the master and data coming into the master. So you can use MOSI and MISO simultaneously. And then it's synchronous, so it uses like the shared serial clock for synchronization between the slave device and the master device. And just as a quick note, there's other topologies also that can be used with SPI. Any questions on this? So for start of the communications, you would pull the chip select for whichever device you want to talk to low. So by default, the chip select would be high, and then when you want to talk to a certain device, the master will pull it low to indicate that it's starting communications. And then you have clock. So serial clock will toggle to like clock data in and out of the MOSI and MISO lines. And then you have CPOL, which is clock polarity, and CPHA, which is clock phase settings to determine the serial clock idle state and which edge to capture data on. You guys can look into that. But like the clock, like in this example, is idling low. If you had the CPOL settings like to the other one, then it would be idling high instead. And that just depends on what your device requires. So like if you're writing a driver for some kind of SPI device, you would have to read its data sheet and see. Um, yeah. Okay, I forgot to mention this. So yeah, there's different SPI modes which you guys can look into, and that basically has to do with CPOL and the CPHA settings. So in the data sheet, it will say like what the clock should be um, idling to, and that'll tell you what to set CPOL to. And then also it'll tell you like, remember how I mentioned where the transmitter would want to change data on one specific edge of the clock cycle, and the receiver would want to sample the data on another edge. So CPHA just changes the phase to do that, like so that way you can either have the master sending data on the rising edge and the slave device samples it on the falling edge, or you can have it the other way around where the slave device samples it on the rising edge and the master sends it on the falling edge. And so that's why you need the phase to make sure that like you're able to do that properly. So data is typically set in either 8 bits or 16 bits, but it's configurable. And obviously, like there's very little or no overhead since like I just mentioned, the way you know it's starting is chip select, so you don't have like a start or stop condition like you did with other protocols. You also don't have addresses, so you're just sending like pretty much just like the raw data that you want to actually send. And then for the end of communication, instead of having a stop bit, the master just pulls the chip select back to high, which tells the device that it's done communications. And advantages and disadvantages. SPI's really high speed, um, since it's less overhead due to chip select and full duplex. And also like the bus, like you're usually able to get like good speeds. Like I think SPI can do up to like 1 megahertz, 25 megahertz. Well, I think that's like the like fast SPI, right? It's like a standard SPI. Not sure. It's really fast. It's faster than UART and I2C. Um, and it's very simple in implementation. But disadvantages is it requires another pin for chip select for each slave device. So like if you're designing like a chip and you have 7 different um, devices, first of all you have like the serial clock, MOSI, and MISO. So that's already 3 wires that you have to route to each device. And then you have 7 different clock, or not clock, 7 different chip select wires to route to every single device. So if you had seven slave devices, that's 10 wires now in total that you have to deal with. And your master, like your MCU, also needs to have enough chip select pins to handle all those different devices. Like you can't just because you only have a certain amount of pins. Like you can't have infinite pins. Um, so you're not able to have as many like slave devices on one SPI line unless you do some kind of way to get around having one chip select per device. Yeah. Any questions? Oh, yeah.
Another question.
Yeah.
So, unlike I2C, is my voice echoing?
Sorry.
Is my voice
Not to me.
echoing? Okay. Yeah. So, unlike I2C, there's SPI.
It depends on the MCU you're using for the master. So you can have as many slaves as you have chip select lines. Like the RM46 has 5 different SPI buses, and like each of them have like it's like 0 to 4. I'm pretty sure like the most one of them has is like 4-ish or 5-ish. Yeah. So like 0 to 5. RM46 has like 0 to 5-ish per SPI bus. So that would only be able to like have 5 SPI sleeves.
SPI, the MCU is always going to be like the controller.
Yeah. Usually when you say like peripheral, that's usually like referring to a slave. But you can have like with I2C you can have like a slave be both the master and the slave. Um, yeah, like another device that's both a master and a slave on the bus. Sorry, could you repeat that? Like, I feel like because
That would be very complex.
yeah, that'd be like kind of like weird because peripherals like slave devices like they should be standalone. Like if they're dependent on another device that they need to communicate with, then like why wouldn't they be manufactured together? Uh, but like if you're saying like otherwise like if it's a master that needs to like coordinate these, then yeah, it would need to like read data from one and then use that to like send data to another. If that's
All right. Yeah. That makes sense. Thanks.
okay,
I have a question.
yeah,
How fast
like the actual lines, yeah. So usually ideally like when you're designing the board, like the person who designs the board. Well, I should have mentioned this board. If you're designing like a board and it has like UART or like I2C and like SPI lines, like it's a good idea to put like test points on stuff like serial clock, MOSI, MISO chip select, so that when you are debugging it, like you can probe those test points and get signals like this, and that can help you with debugging because you're able to see the signal. Um, yeah, and
Usually when you're debugging, you will have like let's say an oscilloscope or a logic analyzer that would and you would connect to the probe points that I mentioned, and usually when you send it, um, the logic analyzer or oscilloscope will essentially show you like how the electrical signals are changing. And so, for example, in the picture above here, image from like a logic analyzer, it's saying, oh, the let's say the SCK line went high and low, and
yeah, and then if you're using like a oscilloscope, you can also see um, how like clean the signal is. So like I mentioned with like I2C, like if you have like your pull up resistor is like a bad value, you could get like line you could get signals that like aren't clean, and so that's why it's causing issues because they're not being able to like be interpreted properly. Like maybe it's not even reaching up to like 3.3 volts. It's like it's only able to rise to like 2.4 volts before it gets pulled down again, and so you just never reach a one. You could debug it with like using an oscilloscope and probing that test point to see what the value is. And yeah. um, with an oscilloscope, you can set like a trigger and set it to single mode. So like you can set like the trigger to when uh, chip select is pulled low, below like a certain voltage. So you set the trigger to that level, and then you put it on single mode. And then it will just like run until it sees that this chip select was pulled below this level, and then it will basically like give you like a snapshot like this, like a certain number of seconds like before and after it went low, and just show you like a snapshot of what all the signals looked like at that time. Yeah, and same with a logic analyzer. Like you can see there's a play button here. When you press that button, it turns into a stop button. So you just pause it and you go back and look at the signals. Any other questions? All right. If you guys have any other questions, you can just like always ask it in firmware general. Other than that, thank you guys for coming. Uh, Hopefully it was helpful.